Forget about dusty textbooks and, those endless boring calculations. Today, we're going to dive into the story of linear algebra. And I don't mean as some math problem we have to solve, but as this incredibly powerful way of seeing structure and transformation and real insight in a world that's just full of complexity. So here's our game plan. We're going on a 5-part journey. We'll start with a really simple, practical problem, and then with each step, we're going to climb this kind of ladder of abstraction. We're moving from just crunching numbers to this grand unified theory that honestly powers so much of our modern world. All right, first up, let's solve some problems. We're going to start where linear algebra itself began, with a situation that's, well, pretty messy. Okay. Just look at this. It's a tangled web of equations, right? A classic system of linear equations. It's confusing, it's disorganized, and you just know you're going to make a mistake trying to solve this thing by hand. This, right here, this is the feeling of chaos. But what if there was a better way to see the actual structure hidden inside all that mess? And boom! This is the first big idea. We can take that entire messy system and pack it into this single elegant grid. The augmented matrix. Look at that. All the information is still there, but now it's structured, it's clean, and it's totally ready for us to work with. This is basically our puzzle board. So, how do we actually solve the puzzle? Well, it turns out there are only 3 simple legal moves. You can swap 2 rows, you can multiply any row by a number, as long as it's not 0, or you can add a multiple of one row to another one. That's it. Seriously. With just these 3 operations, we can systematically simplify any matrix to reveal its secrets. And after we do all that simplifying and get the matrix into its most basic form, one crucial number emerges, the rank. It's just the number of non-zero rows you have left at the end. But this number, this is the true essential dimension of the system. It tells us everything, from whether a solution even exists to how many solutions there are. It's a huge deal. Okay, so matrices are great for organizing calculations. We get that. But what are they actually doing? I mean, what's really going on? To find out, we need to look past the numbers and start seeing the geometry at play. Turns out every square matrix has this special number hiding inside of it. It's called the determinant, and you can really think of it as the matrice's geometric soul. It's not just some random calculation. It's the single value that tells you the entire story of the transformation in one go. And the idea is actually beautiful and simple. The absolute value of the determinant tells you exactly how much the matrix stretches or squishes space. So if the determinant is 2, it doubles the area or volume. If it's 0.5, it cuts it in half. It's a literal scaling factor for the whole universe of our vectors. But wait, there's more. The sign of the determinant tells you how it transforms space. A positive determinant means it keeps the orientation. Think of it like a rotation. But a negative determinant, that means it reverses the orientation, flipping space inside out like a mirror image. And if the determinant is 0, well, space gets totally collapsed into a lower dimension, and you'll lose everything. So we've seen matrices as tools for calculation and as geometric actions. Now, we're going to go a level deeper and uncover the hidden connections that really define a matrice's fundamental character. So what is it that makes a matrix special? What makes a transformation clean, complete, and perfectly reversible? It turns out there isn't just one answer. There are like a dozen of them. And amazingly, they're all connected. And here it is. Welcome to one of the most powerful ideas in all of linear algebra, the invertible matrix theorem. Now, don't think of this as some list to memorize. Think of it as a checklist for a perfect transformation. And what's so magical about it is that if any one of these things is true, then all of them have to be true. A non-zero determinant means you have full rank, which means your columns are independent, which means you don't crush information down to nothing. It's all or nothing. So even in a really complex transformation, are there any directions that stay simple? The answer is yes, and we call them eigenvectors. They are the special vectors that don't actually change their direction when the matrix hits them. They just get stretched or shrunk. And the amount they stretch by, that's their eigenvalue. Finding these is like finding the secret stable axes of a transformation. It's where the action is simplest. All right, get ready to take a pretty big leap with me here. We've been thinking about vectors as, little arrows in space, but what if they could be something else entirely? I mean, really think about that. What if the rules we use for adding and scaling arrows could apply to other things? Could a polynomial be a vector? What about a continuous function? Well, the answer is a huge, resounding yes. And believe me, it changes everything. This brings us to the incredible concept of a vector space. It turns out that pretty much anything that follows those simple rules of addition and scaling can be treated like a vector. That means polynomials, functions, even other matrices. They can all live in a vector space. And all the tools we've built up, rank, independence, transformations, we can now apply to all of these things too. So what keeps these abstract spaces from just becoming pure chaos? Dimension. It's the crucial point. Just like you can't have 3 independent arrows on a flat 2D plane, you can't have 3 independent polynomials in a 2-dimensional polynomial space. Dimension is the fundamental law that governs all vector spaces, no matter how weird or abstract they might seem. Okay, we're in the home stretch. For our final section, we're going to take all of this beautiful, abstract theory and use it to solve a very real and what seems like an impossible problem. So here's the situation. You've got real-world data, and real-world data is always messy, right? The points just don't line up perfectly. You try to model it with an equation, ax equals b, but because of all that noise, there is no exact solution. The system is inconsistent. So what do? Just give up? No way. We use geometry. If we can't hit our target vector b exactly, we do the next best thing. We find the closest possible point to it. And how do we find that? With an orthogonal projection. The best way to think about it is like finding the shadow of our target vector onto the flat plane of all possible answers. That shadow is the best possible approximation we can get. It's so elegant. And this beautiful geometric idea gives us a concrete formula, the normal equations. Now, this isn't just some random collection of symbols. This is the payoff for our entire journey. It uses the deep structure of the matrix to solve that impossible problem and find the line of best fit through messy data. This right here is the engine that powers so much of modern data analysis. And what's the final piece of the puzzle that guarantees this all holds together? It's the rank nullity theorem. You can think of it like a fundamental accounting principle for dimensions. It says that for any transformation, the dimensions you start with are conserved. They either become part of the useful output, that's the rank, or they're part of the input that gets completely crushed down to 0, that's the nullity. No dimension is ever truly lost, it's all accounted for. And so we end up right back where we started, moving from simple calculations to really profound insight. We've built this amazing framework of spaces, transformations, and projections. So the question I want to leave you with is this. How does this elegant unified story of structure power nearly everything in our technological world, from the algorithms running on your phone to the very laws of physics itself?